Two galaxies are tearing each other apart in a silent, beautiful explosion of light. This is the Antennae Galaxies, and what you are seeing is not a static picture, but a cosmic laboratory in violent motion. By the end of this journey, you will understand 25 of the strangest secrets hidden within this collision, from stars flung like cannonballs to invisible monsters feasting at its heart. How can a place of such destruction also be a nursery for newborn worlds? And what does this chaotic dance tell us about our own galaxy's past? What feels more profound to you, the order of the universe or its beautiful chaos? The very arms that give these galaxies their name are the first and most spectacular clue to the violence unfolding. Look at the image and you will see two sweeping, graceful arcs stretching far out into the blackness. These are the tidal tails, and they are not static arms like those of our own Milky Way. They are rivers in motion, colossal streams of stars, gas, and entire star clusters that have been ripped from the hearts of the galaxies and flung into the void. The force responsible is the same one that causes ocean tides on Earth, but amplified to a truly cosmic scale. As the two galaxies swing past each other in their slow-motion collision, their immense gravitational fields pull and stretch each other, much like the moon pulls on our oceans. But here, the pull is so violent it does not just create a bulge, it creates an escape. Millions of stars are slung outward, not in a random explosion, but in these elegant, curved trajectories that trace the gravitational history of the encounter. To grasp their scale, picture this. Each of these streaming tails is hundreds of thousands of light-years long. Our entire Milky Way galaxy could fit comfortably within the span of just one of them. They are a permanent scar, a fossil record written in starlight, showing us the precise angle and ferocity of the initial galactic collision that began hundreds of millions of years ago. Simulations show this process in action, revealing how over countless millennia, the gravitational dance pulls these immense structures out like cosmic taffy, leaving behind a visible testament to the fact that galaxies are not immutable islands, but dynamic structures that can be torn apart and reshaped by their own interactions. But within those violent, stretching tails lies a second, even more profound phenomenon. The chaos is not just destructive, it is profoundly creative. All that gas and dust ripped from the galaxies does not simply drift away. Instead, it becomes caught in immense shock waves and gravitational eddies, compressing into knots of unimaginable density. And in these knots, something spectacular ignites. We call them superstar clusters. Imagine a single cloud of cosmic material, only a few dozen light years across, suddenly lighting up with the fire of not just one or two new stars, but tens of thousands, even hundreds of thousands, all born in a single furious burst. This is not a gentle stellar nursery, it is a stellar explosion of creation. The density is almost incomprehensible. If you were to place one of these infant clusters at the location of our nearest stellar neighbor, Proxima Centauri, the night sky from Earth would be filled with stars brighter than Venus, a dazzling, crowded firmament from a single point of light. These superstar clusters are the universe's ultimate maternity wards, operating at a scale and intensity we simply do not see in quieter galaxies like our own. And their significance stretches far beyond this one collision. Astronomers now believe we are witnessing the birth of globular clusters. Those are the ancient, dense balls of hundreds of thousands of stars that orbit our Milky Way like loyal, ancient sentinels. For centuries, we have wondered how these perfect, spherical cities of stars came to be. They are so old that all their massive, bright stars have long since died, leaving behind quieter, longer-lived suns. Their origin story was a mystery locked in the deep past, but here in the Antennae we have a front-row seat. We are watching in real cosmic time the violent, messy process that forges these celestial jewels. The superstar clusters we see blazing today are the infant versions of those ancient globulars. Given billions of years to settle, their stars will relax into the familiar, tight sphere, and the cluster will cruise through intergalactic space as a fossil of this colossal collision. So we are not just seeing a disaster, we are witnessing the creation of permanent cosmic architecture, the very building blocks that will persist long after the galaxies themselves have finished merging. Those newborn superstar clusters shine with visible light, but the antennae's true violence is revealed in a spectrum our eyes cannot see. Scattered across the collision are dozens of mysterious, searing pinpricks of X-ray energy. Astronomers call them ultra-luminous X-ray sources, or ULXS for short. Each one is a cosmic paradox, a beacon that defies easy explanation. Think of a typical black hole formed from a single dying star, what we call a stellar mass black hole. It pulls in material from a companion star, and as that gas spirals in, it heats up and glows in X-rays. We understand that process, but these ULX sources are different. They are not just a little brighter, they can be 10, 100, even 1,000 times more luminous than that expected process should allow. Yet they are not the gargantuan, galaxy-shaking engines at the centers of galaxies, known as active galactic nuclei. They are something in between, point-like objects of impossible brilliance. The Antennae Galaxies are a veritable treasure map of them, one of the richest hunting grounds we have found. So what exactly are we looking at? The leading theories are as fascinating as they are extreme. One possibility is that we are seeing a new class of object, an intermediate mass black hole. This would be a monster with the mass of hundreds or thousands of suns, more than a star but less than a galactic giant. It is the missing link in black hole evolution, and its powerful gravity could naturally explain the outrageous X-ray output. Another equally wild idea is that these are ordinary stellar black holes caught in a moment of cosmic gluttony. They are feeding on their companion stars at a rate so frantic, so far beyond what theory thought possible, that the infalling material creates a thick, shroud-like disk that contains the explosive radiation and directs it into powerful beams like a cosmic lighthouse on overdrive. This is called super-Eddington accretion, a state of violent excess. Studying these sources in the chaotic environment of the antennae is crucial because the collision itself may be creating the perfect conditions for them to form and feast. The sheer abundance of dense gas and frequent stellar interactions provides an all-you-can-eat buffet for these hidden monsters. Each ultra-luminous X-ray source is a question mark burning in the void, and by decoding their nature here, we unlock secrets about the life cycles of black holes and the extreme physics that govern the most energetic corners of our universe. Yet the most ferocious engine of creation lies not in the graceful tails, but in the brutal heart of the collision itself. This is the overlap region where the two galactic disks are not just passing by, but physically plowing through one another. Here, the chaos reaches its absolute peak. Imagine two immense clouds of interstellar gas, each light years across, slamming together at speeds of hundreds of kilometers per second. It is not a gentle merging, it is a head-on cosmic traffic accident of unimaginable scale. The shock waves from these collisions compress the gas violently, squeezing it into knots so dense and hot that they ignite not just stars, but entire generations of them in a frantic, explosive burst. This region is the ultimate stellar pressure cooker, a place where the forces of destruction are directly and instantly converted into furious creation. But there is a profound irony to this brilliant chaos. To our optical telescopes, much of this action is hidden. The very process of making so many stars also creates vast amounts of dust, the fine, sooty debris from stellar furnaces. This dust acts like a thick cosmic fog, shrouding the overlap region in darkness and blocking our view of the newborn stellar giants within. To see the true heart of this collision, we must look with different eyes. Infrared and radio telescopes are the keys. Infrared light, with its longer wavelengths, can pierce through the dust clouds, feeling the warmth of the hidden stars and nurseries. Radio waves map the distribution of cold hydrogen gas, the raw fuel for all this star formation. When we combine these views, the hidden truth is revealed. The overlap region is not just active, it is a maelstrom. It contains some of the most intense star-forming knots known in the local universe, a hidden metropolis of massive, brilliant stars being born at a staggering rate. This discovery of a hidden population of colossal stars changes everything we thought about this collision's timeline and its future. These massive stars live fast and die young. They burn through their nuclear fuel in only a few million years, a cosmic blink of an eye. Their inevitable fate is to explode as supernova. So, the furious star formation we are witnessing in the overlap region today is essentially planting the seeds for its own apocalyptic future. In a few million years, this zone will not just be a nursery, it will become a graveyard. A wave of supernova explosions will ripple through the region, far more concentrated and simultaneous than anything seen in a normal galaxy. Each blast will blast outwards, heating surrounding gas, enriching it with heavy elements forged in stellar cores, and triggering yet more rounds of star formation in a self-perpetuating cycle of violence and rebirth. The overlap region, therefore, is a ticking clock. We are catching it at a single, spectacular moment in a much longer story. A story where the galaxy's own furious birth pangs will soon give way to a storm of stellar death, forever reshaping the landscape of this epic merger. This furious stellar nursery also creates the conditions for a different kind of cosmic escape artist. Amid the chaos of the overlap region, where stars are born in dense clusters, a brutal game of gravitational pinball is underway. When stars pass perilously close to one another, or more likely, near a dense binary star system or a black hole, the intense gravity can act as a slingshot. One star in a pair might be captured while the other is flung away at a truly staggering speed, possibly thousands of kilometers per second. These are hypervelocity star candidates, cosmic cannonballs shot from the galactic core. To understand that speed, a star like this could travel from Earth to the Moon in under a minute. It would possess enough kinetic energy to break free from the gravitational pull of the entire merging galaxy system, destined to sail alone through the intergalactic void forever. The Antennae, with its dense, chaotic heart, is a perfect factory for such events. The challenge is spotting them. Confirming a single hypervelocity star in that crowded, turbulent maelstrom is like trying to track one specific grain of sand in a hurricane. Its motion must be disentangled from the orbits of billions of other stars, all swirling in the violent dance of the merger. Yet if we could confirm them, these runaway stars would be more than just celestial curiosities. They would be direct tracers, forensic evidence of the extreme gravitational interactions happening in the densest parts of the collision. Each one would tell a story of a close encounter with a massive, unseen object, helping us map the hidden population of black holes and dense star clusters in the core. Their very existence and their trajectories would provide a unique snapshot of the forces at play during this brief, violent chapter in the galaxy's long merger, offering clues we simply cannot get from observing the calm, orderly motions within a galaxy like our own. But the ultimate gravitational monsters are not these stellar cannons or bright X-ray sources. They are the silent giants at the very centers of the two original galaxies. Every large galaxy is believed to harbor a supermassive black hole in its core, millions or even billions of times the mass of our Sun. The question in the antennae is, what are those two black holes doing right now? Are they sleeping, or are they feasting on the banquet of chaos the collision has provided? Evidence from the Chandra X-ray Observatory points to a thrilling possibility. Deep within the dusty hearts of both galactic nuclei, astronomers have detected two incredibly bright, hard X-ray sources. This specific type of high-energy light is the signature of a superheated accretion disk, a swirling maelstrom of gas and dust being torn apart as it spirals into a black hole's event horizon. In other words, these are the screams of matter being consumed. What this suggests is that we are not looking at one, but two active galactic nuclei, two supermassive black holes that have been woken from their slumber by the immense influx of gas driven inward by the galactic collision. They are both actively feeding, shining as brilliant beacons in the X-ray sky. This is a monumental discovery. If confirmed, it means we are witnessing the early stages of a binary supermassive black hole system. These two unimaginably dense objects, each governing the core of its own galaxy, are now locked in a mutual orbit as their host galaxies merge around them. They are dancing a slow, inevitable waltz drawn together by gravity and the drag of surrounding gas and stars. Over hundreds of millions of years, that dance will tighten. They will spiral closer and closer until finally, in an event of cataclysmic power, they themselves will collide and merge. That merger will be the most violent event in the universe since the Big Bang, shaking the very fabric of spacetime itself and sending ripples called gravitational waves out across the cosmos. To see such a system in its active, feeding stage is like finding a fossil that is still alive, giving us a front row seat to a process that will culminate in a titanic release of energy we are only beginning to understand. This furious cycle of stellar birth and death should leave behind a graveyard of supernova remnants. We expect to see the ghostly, expanding shells of gas, the visible echoes of those massive stars exploding at the end of their short lives. Yet when astronomers look closely at the antennae, they find a curious absence. The number of classic shell-like supernova remnants is surprisingly low, far fewer than the intense star formation rate would predict. It is a cosmic crime scene where the expected evidence has gone missing. So where did all the remnants go? The answer may lie in the sheer violence of the environment itself. In a normal, quiet galaxy, a supernova blast wave expands into relatively placid space, creating a distinct bubble-like structure that can persist for tens of thousands of years. But in the antennae's turbulent overlap region, space is anything but placid. It is filled with dense, roiling clouds of gas and crisscrossed by powerful shockwaves from other nearby stellar explosions and intense stellar winds. A newborn supernova remnant expanding into this chaotic medium would not form a clean, round shell. Instead, it would be shredded, distorted, and overwhelmed almost immediately, its structure broken apart and mixed back into the frenzied interstellar soup before our telescopes can clearly identify it. The violence that creates the stars also erases the markers of their death, but the story does not end with missing shells. Astronomers have found something else, a different signature of stellar demise. Scattered through the collision are objects known as pulsar wind nebulae. Imagine the core of a massive star that has collapsed not into a black hole, but into a city-sized, rapidly spinning neutron star, a pulsar. This cosmic dynamo spins with unbelievable speed, whipping its magnetic field around and accelerating particles to nearly the speed of light. These particles stream out, inflating a glowing bubble of high-energy radiation within the surrounding wreckage. A pulsar wind nebula is not the blast wave from the initial explosion. It is the ongoing, energetic aftermath, a powerhouse bubble being fed by the spinning corpse at its center. Their discovery here is a vital clue. It suggests we may be catching the stellar death cycle at a specific moment. The classic shell remnants from the earliest supernova may have already been disrupted and vanished, while the pulsars from more recent explosions are now active, lighting up their own distinctive nebulae. We are not seeing a lack of stellar death, we are seeing a different phase of it, one dominated by these long-lasting, energetic engines. The environment is so extreme it filters what we see, hiding one form of evidence while revealing another, forcing us to listen for the spinning heartbeat of dead stars instead of looking for their fading echoes. All that concentrated violence has to go somewhere. The combined fury of countless supernova and the fierce stellar winds from those short-lived, massive stars does more than just light up the galaxy, it fundamentally reshapes it. This is the phenomenon of starburst-driven winds, and in the antennae, they reach a truly apocalyptic scale. Think of a single supernova, an explosion that outshines its entire galaxy for a few weeks. Now imagine not one, but hundreds, even thousands of these cataclysms going off in a relatively small region of space over a few million years. Each blast pumps colossal energy into the surrounding gas, heating it to temperatures of millions of degrees. This superheated plasma has immense pressure, and with nowhere else to go, it erupts outward. It is a hurricane, but one where the storm clouds are made of seething, ionized gas, and the winds blow at hundreds of kilometers per second. These are not gentle breezes, they are galactic-scale evacuations. These winds act like a cosmic pressure washer, scouring the galaxies of their very lifeblood. They sweep up vast reservoirs of the cold hydrogen gas needed to form new stars and literally blow it out of the galactic disk, sometimes clear out into the intergalactic void. They also carry with them a precious cargo, heavy elements forged in the hearts of stars and scattered by their explosive deaths. Elements like carbon, oxygen, silicon, and iron are launched into the emptiness between galaxies. This process creates a profound feedback loop. The starburst creates the wind, and the wind, by removing the fuel, eventually shuts down the starburst. It is the galaxy's own self-regulating mechanism, a way to prevent it from burning through all its gas in one frantic, unsustainable burst. But the consequences echo far beyond the antennae itself. That enriched material blown out by these winds does not simply disappear. It seeds the vast, thin ocean of gas that floats between galaxies, the intergalactic medium. Future generations of galaxies forming billions of years from now will draw from this enriched reservoir. The iron in your blood, the calcium in your bones, every heavy element that makes planets and life possible, was created in stars and distributed by processes just like this. So these galactic hurricanes are not merely destructive, they are essential recyclers on the grandest possible scale. They are how a single, violent collision contributes to the chemical evolution of the entire cosmos, ensuring that the ashes of dead stars become the building blocks for new worlds and perhaps new life in the distant future. But the fuel for all this stellar fury begins as something cold and dark. Before there are stars, there are molecular clouds, vast and silent structures drifting through the galactic disks. These are not wispy veils of gas, they are the densest reservoirs of raw material in the universe, dark cocoons of hydrogen molecules, and dust so thick they blot out the light from stars behind them. In a quiet galaxy, these clouds drift in relative isolation, slowly collapsing under their own gravity over millions of years to form a few stars at a time. In the antennae, this peaceful process has been replaced by cosmic demolition derby. The galactic collision has sent shockwaves through the interstellar medium, herding these giant clouds together and accelerating them on chaotic paths. The result is not gentle drifting, it is a series of colossal head-on crashes. Imagine a multi-car pileup on a cosmic freeway, but where each vehicle is a cloud of gas light years across, containing enough material to form millions of suns. When these behemoths slam into one another, the physics is brutally simple. The shock of the collision creates immense pressure waves that race through the clouds. These waves compress the gas, squeezing it into knots of extraordinary density. Where a single cloud might have taken eons to collapse on its own, this sudden, violent compression acts like a trigger, pushing vast regions of gas over the gravitational edge almost instantly. It is a chain reaction of collapse on a scale we rarely see. A single cloud collision can create not just one site of star formation, but dozens, even hundreds, all igniting in a coordinated burst. These are the molecular cloud train wrecks, and they are the direct precursors to the brilliant superstar clusters we see blazing across the merger. The pileup of gas does not just make a few stars, it forges entire stellar cities in one concerted event. So when we look at those dazzling clusters of newborn suns, we are seeing the aftermath of a specific, violent accident, the end product of a cosmic traffic jam that turned cold, dark fuel into the hottest fires in the universe. This relentless pressure cooker of creation may be forging stars of a different breed entirely. In a galaxy like our own Milky Way, when a giant molecular cloud collapses, it follows a kind of cosmic recipe. For every truly massive star born, hundreds of smaller, sun-like stars will also form. This predictable distribution, known as the initial mass function, is like a universal law of stellar demographics. But in the extreme violence of the antennae, that law might be breaking. The sheer violence of the cloud collisions and the incredible density of the gas may be skewing the recipe, producing a far greater proportion of stellar giants. Astronomers call this a top-heavy initial mass function. Instead of a few massive stars sprinkled among countless smaller ones, the stellar nurseries here might be churning out heavyweight champions at an alarming rate. Think of it like a town's birth records. In a quiet village, you would expect mostly average-sized babies, with the occasional exceptionally large one. But in the antennae, the records would show a bizarre trend where for every 10 babies born, 8 are giants. This is not just a statistical quirk, it has profound consequences for the entire galaxy. Massive stars are the universe's great accelerators. They live fast, burning through their nuclear fuel in just a few million years, and die young in spectacular supernova explosions. So, if the antennae is truly producing an overabundance of these stars, it means the timeline of this galactic merger is being supercharged. The galaxy is essentially fast-forwarding through its own chemical evolution. Each massive star is a factory for heavy elements, forging carbon, oxygen, iron, and more in its core, and then scattering them across space in its death throes. A top-heavy population means this enrichment happens faster and more furiously, seeding the galaxy with the building blocks for rocky planets and potentially life much sooner than in a calmer environment. But it also means the feedback, that galactic hurricane of stellar winds and supernova blasts we discussed, becomes exponentially more powerful. The galaxy is not just shaping itself, it is doing so with a sledgehammer instead of a chisel, driving its own evolution at a breakneck pace that could leave it looking very different very quickly compared to mergers that take a more measured approach. The violence in the antennae is not confined to brilliant pinpricks. A deeper mystery permeates the entire collision zone, a faint, pervasive glow of hard X-rays. This is not the sharp, focused light of an ultra-luminous source, but a diffuse, ethereal fog of high-energy radiation that blankets the star-forming regions. It is as if the entire galactic battlefield is shimmering with an invisible, deadly heat. This glow presents a fascinating detective story for astronomers. What could possibly produce such a widespread, uniform bath of energetic particles? There are 3 leading suspects, each telling a different story about the merger's hidden population. The first possibility is a cosmic crowd. Imagine millions of faint X-ray binaries, each a quiet pairing of a neutron star or black hole slowly siphoning material from a companion. Individually, each binary is too dim to see at this distance, but collectively, their combined whisper-thin X-ray signals could blend together into this soft, universal glow, like the distant, indistinguishable murmur of a vast crowd. The second suspect is even more numerous. The antennae's furious star formation has created, and will create, an immense population of stellar corpses, white dwarfs, and neutron stars. Many of these remnants are still active, accreting material or simply blazing with leftover heat. Their integrated light, a sort of background hum from a galaxy-wide graveyard, could be the source of the haze. The third, and perhaps most dramatic, possibility points back to the galactic winds. Remember those hurricanes of superheated gas blasting out from the starburst regions? Those chaotic outflows are filled with magnetic fields and shock waves, perfect environments to act as natural particle accelerators. Charged particles like electrons could be whipped to nearly the speed of light within these winds, and when they spiral around magnetic field lines, they emit hard X-rays. In this scenario, the diffuse glow is not the light of stars or their corpses, but the scream of the interstellar medium itself, energized and tortured by the merger's fury. Decoding which source dominates is crucial. It allows astronomers to take a true census of the merger's total energetic output. By measuring this pervasive glow, they can calculate the combined power of all its hidden engines, from the faintest binary to the most powerful wind, painting a complete picture of how a colliding galaxy converts its mass into raw, radiant energy that shapes its own destiny. The ultimate fate of this chaotic ballet is written in the stars themselves. All this spectacular violence, the brilliant clusters and the raging winds, is not a permanent state. It is a single, fiery chapter in a much longer story of transformation. Right now, we are witnessing two beautiful spiral galaxies, each with a distinct disk and swirling arms, in the act of losing their very identities. The gravitational tides that created the long antennae tails are also relentlessly stirring the stars within. Over the next few 100 million years, the orderly, circular orbits of stars in the original disks will be scrambled into random, chaotic paths. The delicate spiral structure will be erased as thoroughly as a drawing smoothed from wet sand. What will be left is something entirely different, a shape born from collision, an elliptical galaxy. Picture a glowing football of stars, a vast, smooth, and featureless cloud of ancient suns. There will be no spiral arms, no dusty lanes, no flat disk. It will be a three-dimensional swarm where stars move in every direction, a settled, quiet retirement after the explosive merger. This is the strange destiny of the antennae. The very forces that are tearing it apart today are the same ones that will forge it into this new, more serene form. Every superstar cluster we see now will either be torn apart or will sink to the heart of this new galaxy, becoming part of its dense core. The hypervelocity stars, if they exist, will be long gone, sailing into the eternal dark. The supermassive black holes at the centers will have finally spiraled together and merged, sending their gravitational waves shout across the universe before falling silent. The antennae, then, is a cosmic chrysalis. We are privileged to see it in its most turbulent, creative, and destructive phase, the brief moment of metamorphosis between two stable states. It begs a profound question about our own home. The Milky Way and Andromeda galaxies are on a collision course set to meet in about 4 billion years. Are we, right now, living in the calm before a storm of similar, unimaginable beauty and violence? Is our own spiral galaxy simply an earlier chapter in the same universal story of collision and rebirth? But the chaos is not just visible or energetic, it is also deeply magnetic. If we could see the antennae with eyes tuned to radio waves, and specifically to the property of polarization, a hidden architecture of pure force would snap into view. We would see vast, intricate patterns of polarized radio emission, tracing the invisible skeleton of the galaxy's magnetic fields. These fields, normally woven in orderly spirals through the galactic disks, have been caught in the ultimate cosmic blender. The collision is stretching, twisting, and knotting them to an almost unimaginable degree. Picture taking two immense, orderly spiderwebs of magnetic force lines and violently stirring them together at near light speeds. The result is not a neat merger, but a turbulent tangle of cosmic spaghetti, where magnetic fields are compressed in some regions and whipped into enormous loops and filaments in others. This magnetic chaos is not just a side effect, it is a powerful player in the drama. These amplified fields can exert tremendous pressure, resisting the collapse of gas clouds and potentially slowing down the very star formation they helped ignite. Conversely, they can also channel and focus material, guiding flows of gas into dense regions. Furthermore, these twisted magnetic fields are perfect natural accelerators. Charged particles like electrons can get caught in these whirling magnetic vortices and be boosted to nearly the speed of light, becoming the cosmic rays that constantly bombard our own galaxy. So this invisible, tangled web of force does more than just look spectacular in radio maps. It actively governs the behavior of the visible chaos, shaping where stars are born and launching the most energetic particles in the universe from the heart of the collision. The colossal tails are not just rivers of escaping stars, they are also cosmic nurseries for entirely new worlds. Within those sweeping arcs, the densest knots of gas and stars are not simply passing clouds, they are fighting for their own independence. Gravitationally bound together, these massive clumps are strong candidates for something astonishing: tidal dwarf galaxies. Think about that for a moment. The same violent gravitational pull that ripped these structures from their parent galaxies is now providing the raw material and the isolation needed for them to coalesce into their own self-contained island universes. It is a profound cosmic irony where the ultimate act of galactic destruction becomes the midwife for brand new galactic birth. These potential dwarfs are not like the ancient, dark matter-dominated satellite galaxies that orbit the Milky Way. They are born from the recycled, metal-rich gas and stars of the original spirals, meaning they could be surprisingly pristine and fertile grounds for planet formation. But their future hangs in a delicate balance. They are caught in a gravitational tug of war. Their own self-gravity is trying to pull them together, to bind them into permanent, stable structures. Meanwhile, the immense pull of the main merging galaxies, hundreds of thousands of light-years away, is still trying to reel them back in. Will these infant galaxies hold on? Some simulations suggest that if they can form enough stars quickly, creating a dense gravitational anchor, they might just make it. They could be flung free, becoming true, independent dwarf galaxies that will orbit the merged antennae for billions of years as permanent, living souvenirs of the collision. Others, however, may not be so lucky. As the main galaxies complete their merger and settle into a new, larger elliptical shape, their gravitational reach will grow. Many of these tidal dwarfs may find themselves slowly dragged back, falling into the galactic core over eons to be swallowed once more. So when we look at those bright knots in the tails, we are not just seeing debris, we are witnessing a cosmic experiment in real time, testing whether chaos can create lasting order, and if new galactic lives can truly spring from a violent death. The hunt for supernova remnants may be challenging, but the Antennae is undeniably a factory for the explosions themselves. Within its chaotic embrace, astronomers witnessed a spectacular and telling death, a star that met its end with the designation SN 2004 GT. This was not a distant, ancient event, but a core collapse supernova that detonated in the Antennae Galaxies in December of 2004. A brilliant flash of light from a single massive star reaching the end of its brief life. Observing such an event in this specific, violent environment is like finding a fresh fossil in an active volcano. It gives us a direct sample of the stars being forged in the merger's crucible. By analyzing the light from SN 2004 GT, scientists could essentially perform an autopsy. The brightness of its rise and fall, the specific chemical fingerprints in its spectrum, all told a story about the star that died, its mass, its composition, and the mechanics of its final collapse. The crucial question was, did this star look like the massive stars that die in placid galaxies like our own, or was it different? The evidence suggested something fascinating. The properties of SN 2004 GT and other supernovas seen in the Antennae indicate they come from stars that are indeed extreme, likely on the higher end of the mass scale. This supports the idea of a top-heavy stellar population. The merger environment, with its dense, turbulent gas clouds, seems to be skewing the recipe toward creating more of these heavyweight stellar champions. Furthermore, the sheer rate of these explosions here is staggering. while only a handful have been caught in the act. Extrapolating from the incredible star formation rate implies that supernovae are likely going off in the antennae far more frequently than in the Milky Way, perhaps every few years or even less. Each one is a titanic pollinator, blasting newly forged heavy elements into the surrounding chaos at incredible speeds. So, while the classic remnants may be hard to spot, the ongoing fireworks show is a constant, visible reminder that the antennae is a place where stellar life cycles are not just accelerated, but amplified, where stars are born big and die young, seeding the future of the merger with the ashes of their spectacular demise. That ceaseless storm of stellar death has filled the sky with more than just light. Wrapping the entire collision, visible only to X-ray eyes, is a faint, shimmering shroud of gas so hot it defies earthly comprehension. This is the hot gas halo, a tenuous atmosphere of plasma burning at over 1,000,000 degrees. If you could feel temperature in space, approaching the antennae would be like flying into the corona of a star, a vast, diffuse furnace on a galactic scale. This is not a solid shell, but a wispy, immense cloud that stretches far beyond the visible stars, a ghostly echo of all the violence happening below. Its origin is written in the fury we have already seen. Every supernova explosion, every screaming stellar wind from those massive, short-lived stars acts like a volcanic eruption, blasting superheated gas outwards. For millions of years, these individual eruptions have been adding their energy to this common reservoir, puff by cosmic puff, until they have collectively inflated this gargantuan, hot bubble that cradles the entire merging system. The gravity of the combined galaxies is just strong enough to hold onto most of this seething plasma, creating a sort of high-pressure atmosphere that the galaxies now swim within. This halo is a galactic energy budget made visible, the total thermal waste product of the merger's most energetic events. But this hot gas is not merely a byproduct, it is a potential future. As this plasma swirls in the halo, it can slowly radiate away its heat, cooling over hundreds of millions of years. As it cools, it condenses, denser blobs can form, and gravity can take hold once more, pulling this recycled material back down into the galactic heart in a phenomenon called a cooling flow. This rain of cool gas could provide the fresh fuel needed to spark new rounds of star formation long after the initial collision frenzy has subsided. However, the story has a twist. The same ferocious stellar winds and supernova shocks that created the halo might also be powerful enough to overcome the galaxy's gravity. Some of this million-degree material may be blowing clear out of the system entirely, lost to the vast emptiness between galaxies forever. So the hot gas halo represents a cosmic crossroads. It is both a reservoir for rebirth and an exit ramp for permanent loss. The fate of this material, whether it falls back or flies away, will help determine if the future merged galaxy remains active for eons or becomes a quiet, red and dead elliptical star city, its fuel spent and its fires gone cold. This beautiful chaos is not an equal partnership. Look closer at the two galactic hearts and a subtle but critical imbalance emerges. The star formation, that brilliant firestorm of creation, is not spread evenly between them. One of the original spiral galaxies is clearly undergoing a far more intense starburst than its partner, blazing with newborn clusters while the other appears relatively subdued. This asymmetry shatters the simple cartoon of two identical galaxies smashing together. It forces us to ask what made these sisters so different in their moment of destruction. The leading theories take us back to the moments before the collision. Perhaps they were never truly identical twins to begin with. One galaxy may have entered this dance with a much richer reservoir of cold molecular gas, the raw fuel for star formation. When the collision triggered the collapse, that galaxy simply had more fuel in the tank to ignite, leading to a disproportionately furious blaze. Another possibility lies in the geometry of the crash itself. Galaxies are not solid balls, they are loose collections of stars and vast clouds of gas. The angle and depth of the collision are everything. one galaxy might have plowed more directly through the densest core of the other, experiencing a more violent compression of its gas clouds, while the other received more of a glancing blow. It is the difference between a head-on car crash and a sideswipe, with wildly different outcomes for the structures involved. Finally, we might be catching them at a specific, fleeting moment in their billion-year waltz. Their orbital dance is not a single impact but a series of ever-tightening passes. The galaxy currently undergoing the fiercer starburst might simply be at the point in its orbit where it is feeling the gravitational squeeze most acutely. Its gas compressed to the breaking point, while its partner is in a slightly more relaxed phase of the loop. This temporal imbalance means the roles could even reverse in the next orbital pass. This lopsided violence is a crucial detail. It tells us that galactic collisions are not clean, symmetrical mergers of equals. They are messy, unpredictable encounters where the original characteristics and precise orbital mechanics of each galaxy write the unique script for their shared demise, a reminder that in the cosmos, even destruction has a deeply personal fingerprint. But the story of star formation here is not one of extremes alone. Beyond the frantic, brilliant overlap region, a quieter revolution is unfolding across the entire expanse of the original galactic disks. The gravitational shockwaves from the merger do not just cause violent pile-ups, they also send out more subtle ripples like a stone dropped into a pond. These are density waves, gentle but immense compressions that travel through the galactic structure. Where they pass, they nudge the vast, quiet reservoirs of cold molecular gas, the ones not involved in direct collisions. This gentle squeeze is just enough to tip the balance. Clouds that might have drifted for another 100 million years without forming a single star are now coaxed into collapse. This has triggered quiescent star formation, a widespread, modest awakening that lights up the galactic suburbs. Instead of the explosive superstar clusters, think of this as the galaxy lighting up street by street, with countless small stellar neighborhoods igniting in a coordinated, peaceful wave. It is a testament to the merger's truly pervasive influence. The violence at the core is undeniable, but its gravitational reach extends to every corner, turning the entire system into a fertile ground for new suns. This process ensures that the legacy of the collision is not just a few brilliant knots of light, but a more complete galaxy-wide renewal, where even the calmest regions feel the distant tremor and respond by quietly kindling their own fires. Infrared eyes reveal a hidden, pervasive ingredient in this cosmic furnace, a blanket of dust so thick it reshapes the very light of the merger. This is not the gentle, cold dust of a quiet spiral arm, it is cosmic soot forged in a tempest. When we look at the antennae in infrared light, the entire system glows with a deep, warm radiance, the thermal signature of countless trillions of tiny grains, each one heated by the furious starlight around it. But the properties of this dust are strange, telling a story of extreme processing. In a normal galaxy, dust is a mix of silicates and carbon-based molecules, like tiny flecks of sand and graphite, often coated in icy mantles. Here, the environment is too violent for such delicate structures. The relentless blast of ultraviolet light from all those massive stars strips away the icy coatings and breaks apart complex molecules. The shockwaves from supernova and colliding gas clouds act like immense sandblasters, shattering larger grains into smaller, hotter fragments and vaporizing some entirely, only to recondense into new, more resilient forms. This means the dust in the antennae is likely hotter, smaller, and chemically simpler on average than dust in common galaxies. It has been through the fire, literally and figuratively. Its distribution is also a map of violence. The infrared glow is not smooth, it is clumpy and brilliant precisely in the overlap region and around the superstar clusters, tracing where the radiation field is most intense. This dust does more than just obscure our view, it plays a critical role in the merger's energy balance. These tiny grains absorb the fierce ultraviolet and visible light from the massive stars, heating up until they glow in the infrared. In doing so, they act as a cosmic radiator, helping to cool the dense gas clouds by converting destructive high-energy light into a gentler thermal warmth. This process can actually help regulate star formation, preventing the radiation pressure from blowing clouds apart too quickly. So this cosmic soot, this product of stellar fury, becomes an essential component of the galactic engine, a gritty, pervasive witness that has been transformed by the chaos and now helps govern its very rhythm. This violent laboratory is not just a spectacle, it is a time machine. The furious processes we witness in the antennae today were once the dominant force shaping the entire cosmos. In the early universe, space was a far more crowded and chaotic place. Galaxies were smaller, closer together, and constantly smashing into one another in a frenzied dance of construction. These colossal mergers were the primary way galaxies grew from modest clumps of stars into the majestic spirals and giant ellipticals we see in the mature universe. But those events happened billions of years ago, far too distant for our telescopes to see in fine detail. The light from those ancient collisions has been stretched into the infrared, faded by unimaginable distances, leaving us with only faint, blurry glimpses. This is why the Antennae Galaxies are such an irreplaceable gift. They are happening right next door in cosmic terms. They are a pristine, nearby template, a living fossil of that violent epoch. By dissecting every detail of this collision, from the formation of superstar clusters to the behavior of its supermassive black holes, we are writing the instruction manual for how our universe built itself. We are conducting a forensic investigation on a current event to solve cold cases from the dawn of time. Every brilliant knot of star formation, every streaming tidal tail, every hidden black hole in the antennae provides a clear, close-up example of a process that was once universal but is now rare. This allows us to take the fuzzy images of galaxies colliding in the deep field surveys of the early universe and say, with much greater confidence, this is what was happening there. We can match the models to the reality happening just 50 million light-years away, and this story is deeply personal. Our own Milky Way galaxy is not a pristine, untouched spiral. Its halo is littered with the shredded remains of smaller galaxies it has consumed, and its thick disk bears the scars of a significant merger billions of years ago. The Andromeda Galaxy is headed for us, a future version of the antennae waiting to happen. So when we study this beautiful catastrophe, we are not just watching the fate of two anonymous galaxies. We are peering into our own past and our own future, understanding that the majestic order we see in the night sky was forged in fires of chaos just like this. Yet for all this detailed observation, a fundamental mystery remains unresolved. We do not know exactly how far away the Antennae Galaxies are from us. This might sound like a minor technicality, but in astronomy, distance is everything. It is the master key that unlocks the true nature of every object we see. Without a precise distance, we are looking at a brilliant picture without a scale. Is that superstar cluster merely bright, or is it astonishingly, record-breakingly luminous? Is that tidal tail impressively long, or is it mind-bogglingly vast? The answer depends entirely on how far away we place the entire system, and here the cosmic rulers disagree. Different measurement techniques point to a frustrating range, placing the collision somewhere between 45 and 65 million light-years from Earth. That is a discrepancy of 20 million light-years, a gap wide enough to fit thousands of galaxies like our own. So why can't we just measure it? The challenge lies in the methods themselves. One common technique uses a class of pulsating stars called Cepheid variables. Their pulse rate is directly tied to their true brightness. By measuring how bright they appear from Earth and comparing it to their known true brightness, astronomers can calculate distance like a standard candle. But in the dusty, chaotic antennae, picking out individual Cepheids is incredibly difficult, and the dust can dim their light, tricking us into thinking they are farther away than they are. Another method uses the brightness of certain types of supernova that occur within the galaxies. Yet even these stellar explosions can be obscured or their light altered by the complex environment. Each technique has its own assumptions and its own vulnerabilities to the very conditions that make the antennae so fascinating. This ongoing dispute is not a failure of science, it is a hallmark of it. It reminds us that even for one of the most photographed and studied objects in the sky, basic facts remain tantalizingly just out of reach. Every calculation about the merger's energy, the mass of its stars, and the power of its black holes carries this subtle asterisk, a quiet acknowledgement that we are still refining our view of this cosmic masterpiece. That faint, shimmering halo of hot gas is not the only sign of a dynamic, living system. Look back at the X-ray map, at those brilliant pinpricks of ultra-luminous energy, and you will notice something strange. They do not shine with a steady, constant light. Many of them flicker. Their brilliance rises and falls over days, months, or years, like distant lighthouses whose beams unpredictably brighten and dim. These are variable X-ray sources, and their flickering is not a flaw in our observation. It is a message. It is the literal heartbeat of these hidden, extreme systems, a pulse that tells us exactly what is happening in the violet space just outside the event horizon of a black hole or the surface of a neutron star. Think of it like listening to a distant engine. A steady hum tells you it is on, but a sputtering, revving, stuttering sound reveals the intricate mechanics of its fuel flow and internal timing. The variability of these X-ray sources works the same way. The speed of the flicker is a direct clue to the size of the engine. A source that changes brightness over a few hours tells us the emitting region is incredibly compact, perhaps only a few times the size of the black hole's event horizon itself. Material swirling in that final, frantic orbit can complete a full loop in mere hours. So changes on that timescale map the geography of the very brink of oblivion. Slower changes over months or years point to larger-scale processes, perhaps changes in the rate of fuel supply from a companion star, or the slow precession of the entire accretion disk wobbling like a spinning top. But the flickering also reveals the texture of the feast. The X-ray light does not come from a smooth, uniform river of gas flowing into the abyss. Instead, it is lumpy and chaotic. The infalling material arrives in clumps and clouds, causing sudden surges in brightness as denser packets of matter are torn apart and heated. Watching these flickers is like watching the monster's digestion in real time, each bright flare a gulp, each dip a moment between mouthfuls. For the ultra-luminous sources, this variability is especially crucial. It helps astronomers distinguish between the two leading theories. Is the incredible brightness coming from a larger, intermediate mass black hole consuming material at a normal rate? Or is it a smaller, stellar mass black hole in a state of frantic, messy gluttony? The pattern and timescale of the flickering hold the answer, acting as a cosmic fingerprint for the mass and feeding style of the invisible object at the center of the storm. So each twinkling point of X-ray light in the antennae is not just a static beacon, it is a conversation, a rhythmic signal broadcasting the intimate, violent mechanics of gravity's ultimate victory over matter. The brilliant collision we see is only half the story. Every galaxy, including our own, is embedded within a vast, invisible cocoon of something we cannot see, touch, or even fully understand: dark matter. This mysterious substance does not emit, absorb, or reflect light, yet its gravitational pull is the cosmic glue that holds galaxies together. In the antennae, these immense dark matter halos are the true architects of the disaster. As the two galaxies plow through each other, their stars and gas slam together in a fiery spectacle, but their dark matter halos do something profoundly different. They are likely passing right through one another, almost ghost-like, with barely any direct interaction. Think of it like two immense crowds passing through each other in a fog. The people, representing the stars and gas, collide, bump, and interact violently, but the fog itself, representing the dark matter, simply mingles and flows, its particles barely noticing each other's presence. This is because dark matter, as far as we know, does not experience the electromagnetic force, the force that causes normal matter to collide, compress, and create friction and light. It only feels gravity, so while the visible galaxies are being shredded, their invisible skeletons are performing a silent, ghostly waltz, slipping through each other's grasp. Yet their gravitational influence is everything. It is the dark matter halos that first drew the galaxies together in this fatal dance billions of years ago. Their immense gravity dictates the speed and trajectory of the entire collision, sculpting the beautiful, sweeping arcs of the tidal tails we see. Astronomers use the precise motions of those tails and the overall movement of the galaxies as a cosmic scale. By measuring how fast the visible material is moving under gravity's influence, they can weigh what is pulling on it. The result is always the same. The calculated mass is far, far greater than the mass of all the stars and gas we can see. The missing mass is the dark matter. The antennae collision, therefore, becomes a unique laboratory. By observing how the visible wreckage moves, we can trace the outline of the invisible scaffolding that guides it all. Does the dark matter distribution match our computer models of such a merger? Does it stay smoothly spread out, or does it clump in ways we did not predict? Each subtle detail in the motion of a star stream or the bend of a tidal tail is a test, a way to probe the nature of this substance that makes up over 85% of the matter in the universe, yet remains utterly hidden from our eyes. The ultimate crescendo of this galactic symphony will be silent, felt rather than heard. While the visible fireworks of star formation will fade over billions of years, the fate of the two supermassive black holes at the galaxy's hearts is a slow, inevitable drift toward catastrophe. If the dual active nuclei are confirmed, then we are watching the opening act of a drama that will conclude with the most violent event possible in our universe since its birth. Right now, these two unimaginably dense objects, each millions of times the mass of our Sun, are orbiting each other at a distance of perhaps a few thousand light-years. But they are not alone in that space. They are swimming through a thick sea of stars, gas, and dark matter. Every time a star swings too close to this binary pair, it can be gravitationally slung away, stealing a tiny bit of energy from the black hole's orbit. This process, over hundreds of millions of years, causes the black holes to spiral closer and closer together. Their dance tightens from millennia per orbit to centuries, then years. In the final stages, they will be separated by just a few light hours, whirling around each other at a significant fraction of the speed of light. This is when Einstein's predictions become spectacularly real. Their immense masses, moving in such a tight, fast orbit, will warp the fabric of spacetime itself, not statically as they do now, but dynamically. They will pump energy into the very geometry of the cosmos, sending out ripples that propagate at light speed. These are gravitational waves. For billions of years, the system will chirp, emitting these ripples at higher and higher frequencies as the orbit decays. Then, in a final, unimaginable flash, they will merge. In a fraction of a second, an energy equivalent to the light of trillions of suns will be released, not as radiation, but as a thunderclap in the structure of reality. This merger will ring the universe like a bell, sending a powerful, specific signal across the cosmos. And we are building the ears to hear it. Future space-based observatories like the Laser Interferometer Space Antenna, or LISA, are designed specifically to listen for the low-frequency hum of merging supermassive black holes. The signal from the final merger of the antennae's black holes, though it lies billions of years in our future, represents the kind of event these observatories hope to detect from countless other galaxies. So every detail we learn today, the masses of these black holes, their spin rates, the density of the environment around them, is not just about understanding this one collision. It is about writing the sheet music for a cosmic symphony we have not yet heard. We are studying the prelude to understand the finale, using the violent present of the Antennae Galaxies to predict the silent, space-time shaking song it will one day sing. The final mystery of the Antennae Galaxies is not in the data, but in our own perception. Gaze long enough at its chaotic swirls and you might see a rose blooming in the void, a cosmic skull staring back, or the delicate wings of a celestial insect. This is pareidolia, the brain's instinct to find familiar shapes in random patterns, and it transforms this distant collision into a personal Rorschach test. We see a rose in the glowing heart, its petals the curved arcs of tidal tails. We see a skull in the dark dust lanes and bright clusters that form hollow eyes and a skeletal grin. It is a reminder that for all our advanced telescopes and complex physics, the human experience of space begins with wonder and imagination. This tendency to see faces and forms in the clouds of a galaxy is the same one that guided ancient cultures to connect stars into constellations, telling stories in the night sky. It connects us across millennia, linking the modern astronomer analyzing X-ray spectra to the stargazer of old seeing a hunter or a bear. So as we conclude this journey through 25 strange phenomena, remember that the antennae is more than a laboratory of extreme physics. It is a canvas. Our scientific pursuit maps its invisible forces and violent history, but our innate curiosity paints it with meaning, drawing a line of personal connection across 50 million light-years. The true beauty of this collision lies in both the profound truths we uncover and the familiar patterns we cannot help but see, proving that to explore the cosmos is to engage both the rigor of our minds and the poetry of our gaze. From the cosmic pareidolia of our own imaginations, we have traveled a path of incredible discovery through 25 strange phenomena in the Antennae Galaxies. We began with the graceful, destructive arcs of the tidal tails and witnessed the furious birth of superstar clusters within them. We peered into the overlap region's hidden stellar factories and hunted for hypervelocity stars shot from the chaos. We discovered ultra-luminous X-ray sources, those flickering beacons of hidden black holes, and felt the searing heat of a million-degree gas halo. We untangled the magnetic spaghetti of distorted fields and pondered the fate of infant tidal dwarf galaxies. We saw how dark matter's ghostly halo guides the entire collision, and how the entire system is a living template for the universe's violent youth. This is far more than a simple crash of two spirals. It is a dynamic, evolving system caught in a single, breathtaking frame of a billion-year movie. It shows us the entire life cycle of galaxies, from their construction in fiery mergers to their quiet retirement as smooth ellipticals, all while recycling the elements of creation into the cosmic void. Every strange phenomenon is a chapter in that universal story, so we turn the question to you. After this journey, which of these 25 wonders resonated most deeply? Was it the stellar cannonballs, the invisible dark matter scaffold, or the silent future song of gravitational waves? Share your favorite in the comments below, and if you want to join us for more deep dives into the universe's greatest mysteries, be sure to subscribe. The cosmos is full of collisions, explosions, and silent, beautiful transformations waiting to be explored.